Okay, you already probably noticed that force video was kind of long. There's a lot of stuff going on with forces in simple harmonic motion. And at the end of the day, while we can nitpick specific moments with forces, we can't really do very much in the broad scheme of things with forces because the acceleration is constantly changing, which means we can't use kinematics to make any long-term predictions. We can do that stuff with energy, but it turns out that this is where energy really shines. Because while we're going to use energy to figure out a lot more than we can with forces, we also don't have to do nearly as much work along the way. So let's start with this vertical or this pendulum going back and forth. I'm going to divide it into 3 different moments. I'm going to say, here's the moment where it's at the furthest left, right there at the equilibrium position, and right there at the furthest right. It's going to go from a gravitational potential, and then ideally, we call this right here our gravitational potential energy equals 0. That's the lowest the pendulum ever goes. That's the lowest a swing ever goes, all those kind of things. So call that 0. Then you don't have to worry about how far it is off the ground or anything like that. It's good enough that we call that 0. So if that's 0, then we don't have any gravitational potential there. All we have is kinetic energy there. And then finally, it goes back up to the other side, and then it goes right back to gravitational potential. This is really easy because the equations that just end up looking like mgh equals 1/2 mv squared. And if you're solving it for velocity, velocity is equal to the square root of 2gh. And if you're solving it for h, it's just v squared over 2g. And basically, that's all there is to pendulums going back and forth. You're either going to find its final height, or you're going to find its velocity at that middle point, and we're done. And it's really just pretty simple energy problems right there. Going to the horizontal spring, it's still pretty easy problems. I'm going to call this one energy spot 1, energy spot 2, and energy spot 3. At energy spot 1, this is when it's maximally compressed, so it would have spring energy there. Then it pushes itself out to the equilibrium position, that's E2, and at E2, that's the rest state. That's where if we stopped it and just left it there, it would stay there because it has no potential energy, and there's nothing holding it in that position. So all of that spring potential has turned into kinetic energy. And then, but because it's moving, it's gonna go back out to E3. It has to conserve the energy, so it starts turning that kinetic back into spring potential. And by the time we get out to E3, we're back to pure spring potential again. So these problems are similarly easy to the pendulum problems because we just have one type of energy that cleanly turns perfectly into kinetic energy at the equilibrium position and then goes all the way back to its original type of energy at the end. So again, typically you're just going to say it's been pulled back this far, find the speed right at the equilibrium position, or we're going to say here's the speed at the equilibrium position, how fast or how far does it move to the left or right type thing. So those problems are going to be easy. We'll just say the spring potential is equal to the kinetic energy. That's 1/2 kx squared equals 1/2 mv squared. The halves cancel. And then if we're trying to get the velocity by itself, it would work out to be the velocity is the square root. Oops, I changed color here for some reason. The velocity would be kx squared over m. And if we're trying to find the displacement of the spring, it's going to look almost the exact same, except it would be mv squared on the top and then k on the bottom. So these problems are pretty simple. There's a little bit more like squared and square roots involved in here because there's a square on each side. But probably the biggest thing to notice is that mass doesn't cancel. Mass is canceled in a lot of our problems, especially energy problems. But I need you guys to remember that it doesn't cancel in spring kinetic energy problems or any problem involving springs. The mass stays in there because mass doesn't exist on the spring potential side. It canceled with pendulums because mass is on both sides, but it doesn't here. All right, the final one is vertical springs, and vertical springs are actually kind of nasty. The reason why they're kind of nasty, first off, let's call this our zero potential gravitational potential spot. This is, again, right here, this is our equilibrium position. So, oops, that's not correct. This is our equilibrium position. So let's go through our motions, or our moments, E1, E2, E3. At E1, you can see that it only has gravitational potential. That's usually if it's starting at the natural length and it's being let go, so the spring hasn't been stretched or compressed. As we get to this position here, it's moving, so it has kinetic energy. The spring has started stretching, so we have spring potential, and we have gravitational potential. And while I drew them all exactly the same size, there's no guarantee that that's actually true. So this one becomes really ugly because at many points between E1 and E3, we have all three types of energy and it gets really ugly. The only good news is if we call this our endpoint, gravitational potential 0, then we only have spring there. So really the only thing that's usually convenient is comparing these 2 points here, the highest point versus the lowest point. And if we do that, we can just say something like mg h is equal to 1/2 mv, nope, that's not true, 1/2 kx squared. It turns out that this h, the height it's up, is equal to the x that it's stretched. So I can cancel out 1h and 1x. But from there, depending on what we're trying to solve for, we can easily solve for x, I suppose. We could say it's something like 2mg over k. But just be really careful in those intermediate moments. We have lots of energies here. If you can solve it, but it's definitely going to require the quadratic formula. So thank you guys so much for watching this video. That's everything you need to know about simple harmonic motion and energy problems.